Welcome, everybody. I'd love to introduce Frank Neffke and the team from the Vienna Combustion Institute. And he'll be focusing on the evolution, the dynamics of innovation and, innovation firms. Welcome.
Well, thank you very much. And thank you for having me. Let me just see if I can share my slides.
Mm-hmm.
Yes, I think you should be able to see this now, right?
Mm-hmm.
Excellent. Yes, so maybe just a very quick explanation of where I'm at. I'm at the Complexity Science Hub, which is an institute that started about 10 years ago in 2016, to be precise. And what it tries to do is to use complexity science or methods from complexity science to make sense of social phenomena. So we are basically a bunch of physicists and computer scientists, mathematicians, working together with people more from the social sciences like myself to try to understand how societies work and maybe also to figure out what we can do to solve societal problems. So within this mix, what I focus on is the question of how do economies learn? So if you think about learning, it's something we do throughout our lives. Individuals learn going to school, at work, and so on. But what I'm more interested in than that is how all of these different individuals, these individual learning trajectories add up to something that would be learning at the collective, so learning at the levels of entire economies. So, and to give you a sense of why that might be important, first of all, knowledge is behind most of the increases in productivity in the economy, but knowledge has also been expanding very rapidly over the last couple of centuries. So this is a very nice work by historians who looked at the books and manuscripts that were available in Europe over a very long time period. And what you see is that knowledge encoded in books and manuscripts grew exponentially. So in the year 500, there are about 10,000 manuscripts. It goes up to 10 million at the time the printing press is invented. And then you go over 1 billion books and manuscripts at the beginning of the 20th century. We have something very similar if you would look at patents in the US. So you have a little bit of a startup period in the 19th century, and then you see that there's an exponential increase in the number of patents that were filed in the US, presumably representing new knowledge, new know-how. And that's actually a challenge. It's a problem that we have to deal with, because there's no reasonable way in which you could say that we as individual human beings have become cognitively much smarter than our ancestors 200 years ago, 2,000 years ago, maybe even 20,000 years ago. So biologically, we still have the same brain, more or less. And the fact that there's now so much more knowledge around means that there's not a single person anymore who could try to comprehend all of it. And that brings you in sort of a different way to Adam Smith, and Adam Smith is the founding father of economics, and his thoughts on the division of labor. So in Adam Smith's work, the division of labor is very important to raise productivity. So if you divide labor, people can focus on specific tasks, and that reduces switching costs. It allows you to invest in dedicated machines for a task. You actually can get onto steeper learning curves, so you might become better at it over time. So in a sense, division of labor in most of economics is a way to become more productive or become more efficient. But in the way I'm trying to tell this story is that division of labor is actually not the way to become more efficient, but it's the way the world deals with this growing global body of knowledge and this limited cognitive capacity at the individual level. Because once that happens, the only thing that you can actually do is you have to divide that knowledge across more and more people. So as the knowledge in the world grows, you end up with an expanding array of experts. So you basically get a system where knowledge, this collective body of knowledge, is sort of distributed expertise across different types of people, from the butcher and the baker down the street to the nuclear physicist and and actuaries, what have you, all these specialist types of jobs that nowadays exist. Actually, David Otto was presenting, I think, in this series a couple of years ago, and had a very nice paper on showing how many new occupations are actually added in the 20th century. So basically showing this division of labor and how it deepens over time. So if you think about economic growth from this perspective, one thing that happens is that you see an increase in the number of tasks. So there's a bunch of limited number of tasks that happened that humanity was carrying out 4,000 years ago, and the number of tasks we're trying to carry out with our economies has just grown tremendously over the past millennia. And that has a number of very important consequences. First, we will need to specialize. So whereas before there was basically one type of specialization, you were maybe a hunter or a gatherer or a farmer. If you look at societies nowadays, there are a large variety of different types of jobs or occupations, and they bundle different sets of tasks. So once you do that, there's actually a second thing that happens, and that is that we become dependent on one another. Because if I specialize in one thing, it means that I don't specialize in all the other things, but they still need to happen for us to produce something. So in essence, I become dependent on other people specializing as well, and preferably in something else than what I'm specialized in. So what happened is that we started working in teams. Now these teams themselves, they will somehow need to be coordinated. So teams, you can put people together in a room, but that doesn't mean that you have a team working. You have to make sure that these teams work together, and also that teams work with other teams. So you need some kind of coordination mechanism. And societies have become pretty good at coordinating knowledge. We've always coordinated knowledge. So one of the things that my group looks at is cities. And cities are one of the oldest devices to coordinate this distributed expertise, basically putting people at very close proximity so that they can coordinate their actions. Later, you see like the villas in ancient Rome. They were not just places to live, they were actually complete productive systems with a division of labor that produced agricultural products, but also some manufactured goods. You see the guilds of the Middle Ages. And in the 19th century, you actually see the breakthrough of the firm as an organizational innovation. So firms are, in this way of looking at it, just a mechanism in which you can coordinate distributed expertise. So if you buy into that story, it actually suggests that we may need to rethink the way we think about human capital. Not the first one to say all these things. So it's not that this is a unique position that I'm putting forward here. And that's also what you see in the literature. There's been quite some interesting work on all of these things, and I'll walk you through some of the aspects of human capital that you would have to change the way you think about it. So the first thing is that if human capital is the expression of collective knowledge as distributed expertise, then it doesn't make much sense to ask how much human capital do you have? So how many years of schooling do you have? Or do you have a college degree, yes or no? But what kind of knowledge do you have? So what is actually the content of your human capital? A second thing that is important is that the returns to this human capital, they only materialize within a specific context. So for instance, if you think of anesthesiologists, they're very highly paid professionals. But if you imagine an anesthesiologist in a place where there's no surgical team, then this anesthesiologist will not be able to do much more than helping people fall asleep. So the value of that skill is much lower in this case, and it only really materializes in an ecosystem, a skill ecosystem, where different people focus on different aspects of production. And the last thing is that you would have to move beyond individuals, right? So these human capital is now something that takes its value in the context of groups, and these groups need to be coordinated. So I'll walk you through a couple of things before I get to the main paper that I will present, which is about this third aspect. So ways in which complementarities have been coordinated. So the first thing, to think of human capital not as a quantity, years of education, but rather as looking at the content of skills. That has happened in work that looked at skill vectors. So in this work, you can think of jobs as bundles of tasks. So a job is basically a unique bundle of tasks that requires a unique bundle of skills. So workers have a bundle of skills, have a vector of skills, and jobs have a vector of tasks. So here, as an example, I show you 3 occupations and then a very short made-up skill vector that shows you how these 3 occupations differ from one another. So manager needs managerial skills and oral comprehension. Web designer needs programming and design skills, and so on. And if you map these skills, you can actually ask how different are 2 jobs. And this is work that started being done in labor economics in the early 2000s. So there are some papers here that are listed here by Polotov and Robinson and Gatman and Schoenberg, who measure the skill mismatch that people experience when they move from one occupation to another by using information that is encapsulated in these skill vectors. And so a little bit later, the same kind of concepts are also used in maybe what's called computational social science, where these skill vectors are not used to calculate mismatch, but rather to look at occupations within skill spaces. So maybe to illustrate that, I think the paper by Catherine Anderson is particularly nice. It's also one of the first. So what she uses is data from an online freelance platform. And on that freelance platform, you can list jobs, and these jobs require certain skills. So you are an employer, and you have a number of jobs that need to be carried out. But you can also sign up as a worker, a freelancer, and then you list the skills that you have. And what Anderson does is she looks at how these skills co-occur within the profiles that workers submit to this platform. And then these spaces tell you which skills are very often co-used by the same worker. So that gives you a depiction of human capital through the lens of a space of skills. The other skill space that she builds is a space where skills are close to each other if they very co-occur within the same jobs. And this is not exactly the same network. So there are differences between these 2 networks. And it turns out that that is important. So one of the main findings of this paper is that having a diverse set of skills, so having skills that are in different parts of this skill space on the left, so these are skills that are not typically combined by the same worker, is associated with higher wages, but only if these skills are also often combined in the same jobs. So they're not combined by workers typically, but they are often used together to perform a particular task. So what is particularly valuable in terms of human capital is having skills that others cannot combine, but that are usefully used together. There is quite a bit of follow-up work on that, using these skill spaces to map human capital in different ways. We recently worked on a paper where we have hierarchical networks, and we express the value of a skill in terms of the length of dependencies within these hierarchical networks. So a skill is more valuable, turns out to be more valuable, if it has a longer dependency network. So if it depends on a bigger tree of precedents. Okay, so that's about the individual level. So at the individual level, if you want to understand what is human capital in terms of these skill vectors. But then if you think about the fact that skills are actually only becoming useful if they are combined with the skills of other people, then you can ask this question about how important are these complementarities between workers. And we also looked at that. So I looked at that a while ago using data, administrative registry data from Sweden. So the Swedish Statistical Office collects data on the entire Swedish population. So you can see the entire career paths, wages, social demographic information about each individual living in Sweden. And you also see where they work, so in which establishment they work, so you know who they work with by implication. And what is very nice about the Swedish data is that you not only know what kind of work they do, so the occupation in the industry in which they work, but you also know the type of education they took in a very detailed way, because in Sweden, the different schools, they send the graduation information to the statistical office, and then it's linked to a personal identifier. Of course, this is all anonymized on the servers of Statistics Sweden. But once you're in that environment, you can analyze these data. And then there's a lot of information on what people actually studied in school. So for instance, there are over 200 different types of college degrees in the dataset. Okay. So how does this actually help you understand anything about complementarities between workers? Well, the idea that is leveraged here is that firms presumably know what they do. So if you ask firms who they want to hire, they will try to hire workers who somehow cover the entire spectrum of knowledge that they require to carry out the tasks that are needed to be carried out by the firm. So in that sense, by looking at firms, you can get a sense of which educations might be complements, so which skills are complements, by looking at how these skills are combined within establishments. So as a toy example, I imagine that there's an establishment that has workers with 3 different types of educations, T, A, and C. Then in that establishment's workers, so the educations T and C, T and A and C all co-occur. So you can count these co-occurrences across all of the establishments in Sweden and plot them as a network where you connect 2 educations if they're more often found together in the same establishment than you would expect by pure chance. So I did this analysis, and what you get then is a network that looks like this, where the colors are broad areas of education, and the symbols reflect the level of education. So the sharper the symbol, the higher the level of education is here. So the triangles are more highly educated than the circles, for instance. So if you zoom in on healthcare, then you see that people with healthcare educations, they very often work with other people that have healthcare education. So doctors work with nurses, but there are also other types of educations that doctors work with, like medical secretaries, which are a business type of education, or people with a degree in psychiatry or psychology. And it makes a lot of sense that you would combine them, because you would need them probably in a hospital to provide care. But they wouldn't necessarily have all the same education. Now, the problem of this approach is that firms do not just hire complements, they also often need just more of the same skill. So a lot of your co-workers are actually not complementing you, they could substitute for you. And you would expect a very different dynamic with substitutes than with complements. Complements would typically be good for you, but substitutes that might be tricky because they could basically do your job. So to measure how substitutable 2 educations are, from an employer's point of view, educations are substitutable if workers with 2 substitutable educations can do the same job. So if you think of occupations, which are bundles of tasks, if 2 educations allow you to perform the same types of tasks, then those 2 educations are likely to be substitutes. So here in this example, education C and K both allow you to become a doctor or a nurse. So those two educations would be substitutes for one another. Okay. So now I build a space. I built two spaces. One where workers that work together, they are likely to be complements, and one where workers could substitute one another because they can do each other's jobs. So if you look at the substitutability network, it looks very different from this co-working network. So you see the same jobs here highlighted, and you see now that doctors work with nurses, as shown in the previous network, but they cannot substitute for one another. Neither can dentists, nor psychotherapists, or medical secretaries. So it makes sense. These jobs are pretty different, but they would come together to provide healthcare. Okay, so there's a long story to get to some of the results that I wanted to get at, because you now can think of complementarity as the degree to which two educations are very often found working together. So workers with two educations, two different educations very often work together, controlling for how substitutable these educations are for one another. So the excess co-working relation compared to the substitutability relation, I'll call that complementarity. Okay. So if you look at complementarity over your working career, then you see that complementarity keeps going up over time, especially fast when you're young in the first years, because then you switch jobs a lot. And it turns out that you match yourself into more and more complementary teams. And that goes on up to 20 years after you left college. So basically, I measure these specializations from the education system. And then I look at to what extent is your education a complement for the education of your coworkers. And it turns out that in that sense, you over the course of your career, you find ever better fitting work environments on average. So what is very interesting is that if you look at wages and how wages develop over your career, they follow a very similar curve. And in this paper, I try to look at to what extent is one causing the other. And the best estimate of this is that the effect of complementarity on wages is of a similar magnitude as the effect of having a college degree. So having complementary coworkers is as important as going to college yourself. But that's actually not the question that I wanted to answer. I wanted to know to what extent is the value of your skills dependent on who you work with. And here you, in Sweden, you see that on average, the value of a college degree is nowhere as high as in the US. And that's because the wage structure of Sweden is very compressed. So on average, a college-educated worker earns about 60% more than a worker with only primary school. But what is interesting is if you divide workers into groups by how complementary their co-workers are to them. So you divide them into quintiles such that the lowest quintile has very few complementary co-workers and the highest quintile has many complementary co-workers. So if you do that, you see that there's a lot of heterogeneity in the returns to a college degree in Sweden. With people without any complementary co-workers, they just earn 18% over the primary school wages. Whereas workers with many complementary co-workers, so in the top quintile, they earn up to 90% over workers with just a primary school degree. And to put that into perspective, this 18% is essentially what workers with just secondary education earn. So the value of your own skills changes drastically depending on who you work with. Okay, so that gets us to the final point. How do we actually manage to coordinate individuals? So how do we coordinate this distributed expertise that is embedded in the heads of people around the globe? And that's the paper that was also announced for today. It's a paper together with Matteo Hartog, who I think is in the audience, Andrés Gómez, and Ricardo Hausmann. So these are colleagues from when I was still at Growth Lab at the Harvard Kennedy School. So paper that took quite a while. We started in 2016 and had a pandemic in between that slowed us down a bit, but it's now finished. So what we try to do here is to find a way to study the effect of new coordination mechanisms that arise in society on how distributed expertise is organized. And if you want to do that, you actually have some pretty heavy data requirements. So first of all, you need very long time periods, because typically these processes in which new coordination devices are developed, like the idea of a firm or the idea of a guild, it develops over a very long time period. The other thing is that you need detailed information on capabilities of the individuals themselves, so that you understand how division of labor would work. So you need microdata, and you need information on complete teams. So I cannot do a sample of the population. I need to know all the different people who work together. So I need to have the full population. So what we came up with as an object to study is patent data from the US Patent and Trademark Office, the USPTO. That's a very long time series from 1790 to 2019. And to add to that information on what individuals actually know, we merged that with the historical records of the US Census. So in both data sets, you have the names and places of residence, so you can merge these two data sets. And that took quite a bit of time to pull off. So this is the US Census records. They're very nice because they have the names, they have the places of birth, they also have the places of residence. And then on top of that, they would show you the occupation and the industry in which people work. And then what we did is we didn't digitize this. We cleaned it up and merged different waves of the census to one another, and we geocoded it. So to give you a sense of what this data looks at geographically, this is the US Census plotted on the map of the US in 1850. And you see that where you guys are on the West Coast, it's basically just the gold rush cities show up there. And if you move forward, you actually see the entire urban system of the US emerge over time. So along the rivers and on the two coasts and in the middle. And what is nice is that you do not just know in each dot how many people are living there, but you actually know for each person their occupation, their industry, the composition of their household, and so on. So then we move to a second data set, the USPTO patent data. And that's also a great data set. It's just the problem was that this was not digitized. So patents have information on the inventors, so the names of the inventors, the places where these inventors live, so the places of residence, and also the firm to whom this patent was assigned, so the owner of the patent in the end. And we interpret that as the firm that coordinated the team or the inventor, managed the inventor that produces patent. Now, we didn't use the patents themselves because the patents are digitized only from 1975 on. We used patent yearbooks, where you have, in each year, all patents are listed with one patent. Each patent has a different line where the inventors, their names, the places of residence are listed, and also the company, if it was assigned to a company, the company's name and location is also mentioned. And then the final data set that we use is a survey that started in 1920 on industrial research labs. So this was a survey by the National Research Council that tried to assess the state of the US economy in terms of the industrial research that existed. And this is these are a bunch of books that describe for all the research labs. They identified the company, the place where this lab was located, and a bunch of other things, but we'll just use this company name. And we use this company name to link this to the patent data to be able to ask question of which firms in these patent data actually own a research lab. Okay. So then the final data source that we use is the patents themselves. Patents do not just list the names and locations of inventors, they also give you some information about the technology that is being patented. And these are technology codes in a specific classification system. And that classification system helps the people at the patent office to search the state of the art when they have to decide whether a patent is novel or not. So in that sense, you can think of these codes that are listed on a patent as an abstract description of the technology that's being patented. So this patent has 6 detailed classes listed on it. Well, it's actually more than 6 digit class, so there's more than a bunch of detailed classes listed on it. I'll call them 6 digit classes, even though some have a couple of extra digits, but most have 6. And if you would just look at the first part of this code, which is sort of the broad technology, it has 2 different classes. And then you can describe this patent as the exact combination of technologies that is listed on the patent. And what I will do is I will use this information to ask, is this patent a novel innovation? So is this a novel combination of technologies? By looking at whether this exact combination of technology classes was ever found on a patent before. And if it's a combination of high-level classes, so broad classes, that is new, then I call it the radical innovation. And if it's just a combination of detailed classes, then it's a more incremental innovation. And again, this is not something that we came up with as a measure of novelty. This is something that others have done before us. Okay. So this gives you a sense of how the data set is structured. We connect a bunch of different data sets together to end up with a data set that has patents, their inventors, the occupations, age, gender, and industry of the inventors, whether or not the patent was assigned to a firm, and whether or not that firm had a research lab or not. Okay. So the last thing that I need to tell you before I get into the findings is that I'm going to show you very simple analysis. Most of it is just an average of a variable and how that average changes over time. So there is one problem with that approach, and that is that the number of patents increases exponentially over time, which means that in the 1850s, I have very few patents. So I have huge confidence intervals. If I show that, if I would divide the data into decades, so the early decades have very imprecise estimates. And then in the late decades, I actually have so much information that I could have split them in much smaller slices. So that makes it a bit hard to choose a time window that makes sense. So instead of choosing a time window, I sort all the patents by the exact date. And then what we did is we created intervals with a fixed number of observations. So as a stylized example, you see below there are 6 patents. The first 3 is 1 observation, and the average time is 1867. And the last 3, they're much closer to each other, but it's also 1 observation. And again, the year for those observations, we take the average year of when these patents were found. So that explains what the graphs will look like. Okay, so then to give you a preview of what we find is that there's a lot going on. Patents increased drastically between 1850 to 1940. Actually, the US in this period goes from an agricultural society to the frontier in science and technology. But there is this transition is not smooth. There's actually a point in time when many of our curves have a very sharp break, and that's in the 1920s. So a range of activities, a range of variables drastically change in the 1920s about who becomes an inventor, the learning curves of inventors, the teams behind inventions, and also the way these teams are organized. So the thing that people are most interested in. And if you think of these as sort of drivers of change, then there are also a bunch of consequences. One is that there is, in the 1920s, there's all of a sudden a very sharp increase in the share of patents that are radical innovations. Another thing that shifts is the geography. So where is most of the inventive activity taking place in the US? That shifts drastically in the 1920s. And you see, for different societal groups, you see a bunch of new obstacles arising that prevent these groups from fully participating in the innovation system of the US as it emerges in the 1920s. So in the 1920s, you basically see the emergence of a new innovation system. Okay, so let me walk you through that. So first, in the inventors, you see the evidence for specialization. As I mentioned before, if you divide knowledge across more and more people, then you would have an increasing number of specialists. What you see is in innovation, there's one type of inventor, one type of background that becomes the driving force of innovation, and that's the engineers. So in the 19th century, most innovations are either by farmers, because there are just a lot of farmers in the US, or by blue-collar workers, craftspeople. But in the 1920s, all of a sudden, you see this takeoff of patents that are filed by engineers. So in the 1940s, there's about 25% of all inventors are engineers. And that's very large, because as a group, they represent just, they represent less than 1% of the workforce of the US. So engineers become heavily overrepresented in innovation in the US. Another thing that you can see is the rise of academic patents, which is closely related. So engineers as basically the science-based innovation, is you also see it in the academic patents themselves, which I here think of as patents that are filed by professors. So you again see this takeoff in the 1920s. And the interesting thing is that even though professors are filing inventions, on patented inventions, that doesn't mean that the universities become very much involved, because most of these patents that the professors file are actually owned by themselves, or they are owned by firms. So in a sense, this is also the first time that you see the types of industry university collaborations that we see nowadays. There are some patents that are owned by firms. So you see a takeoff of university patents. But what is very interesting is that this is not necessarily the universities that you might think of. This is not like the Ivy Leagues or the Ivy League universities. This is basically mainly the universities in the Rust Belt. So Purdue, Iowa State, University of Wisconsin. Stanford is actually very late. It's more of the 1940s, not the 1920s. University of Minnesota, Illinois, and so on. So last thing that you can say about these at the individual level is that it seems that the way individuals learn to become an inventor changes, or at least their learning curves change. So what we looked at here is two variables. One is how complex are the inventions that are being filed? And we take a very simple measure, we just count the number of different technologies they combine. And the other one is asking, the other question we ask is how new are the technologies that are used on the patent? So when was this technology first used? And is this, based on that, we can calculate the age of the technology and ask how new are these technologies? And here you see the learning curves of different cohorts. So you see age on the horizontal axis, and then you see to what extent how many technologies the inventors combine on a single patent. And it's all against their peers. It's all, the question is, how many more technologies do they combine than their peers that are inventing it in the same time period. And then you see the old cohorts from the 19th century. They basically, over time, they invent less and less complex technologies. And that changes drastically in the green line and the red line, which are basically the first cohorts of the 20th century. So they are born in 1880 to 1900, or even 1900 to 1920. So they really start inventing in the 1910s, 1920s. You see something very similar, but even more drastic when it comes to how old or how recent the technologies are that they use. So traditionally, as you age, you use older and older technologies compared to contemporaneous inventors. But that's not the case for the cohorts of the 20th century. They need some time before they actually are able to use the most recent technologies. And then they go well above the others in the cohort, so the older cohorts. So another thing that happens in this time is that innovation shifts from being an individual activity to teamwork. And this is actually something that we know, that in the 20th century, more and more of science and innovation is actually done by teams. So this is a paper that was published in Science in 2007 by Wuchti and co-authors. And you see here for science and engineering, social sciences, and patenting, you see that the share of papers or patents that are filed by teams goes up over time, and the size of these teams also goes up. So to give you a sense of the time period that we're talking about, this is basically on this scale that we are looking at, it's happening over here, so in the late 20th century. And the data that I've been showing you so far is actually much earlier. And what is nice is that it seems to capture this start of the takeoff of team patenting. So if you zoom in on that period, what you actually see is that team patenting, so the share of patents that were filed by teams, was, if anything, slowly declining in the beginning of the 20th century. But that turns around very sharply in 1920, when all of a sudden the share of patents that were filed by teams starts going up very rapidly. And if you look at who is actually working together in these teams, then you can look at 19th century teams, and they're very often people who work together on the shop floor. So machinists with operatives, or machinists with laborers, operatives with carpenters. And there's very often also sort of a difference in occupational standing. So you have a more senior worker with a more junior worker working together on these patents. And that changes very drastically in the period from 1920 to 1945, where basically most teams are teams of 2 engineers. And here, what I leave out is the teams that have exactly the same occupation, because then you wouldn't see anything. You wouldn't see any combinations of different occupations. So the vast majority of teams are engineers with the exact same background, and all other combinations tend to be engineers working with very highly trained other engineers or chemists or draftsmen and so on. So the composition of teams change. So here you see it more in graphs. You see that the age difference goes down. So the difference in seniority also goes down. Same occupation teams goes up. And this is a measure of how similar 2 occupations are. And if you look at that, then you see again this very drastic shift in team composition in 1920, where the teams become more and more homogeneous in terms of the skills that are present in them. So why is this happening? Well, actually, all of this coincides with a change in the way these teams are coordinated. So here you see on the vertical axis, you see the share of team patents, and the different graphs show you how these teams are coordinated. So the red line uses family relations. So basically ask, do two people on the patent share the same last name? In that case, we think that they're probably related. So in the 19th century, even though that's an undercount of family patents, that's the dominant mechanism that we can identify to coordinate teams. And in the 20th century, you see that this shifts to firms, but mostly, and very drastically in the 1920s, to firms with research labs. That's a green line in this graph. You can also express it in a different way. So you can ask, out of all the patents that are either filed by firms or filed by firms with research labs or filed without a firm involved, but here standalone, what is the share of patents that are team patents? And then you see that all of the increase in team patenting that I showed before actually comes from teams that were working for firms or research labs. Because the red line is basically flat. So if you were not working for a firm, then the likelihood that you were working in a team didn't change much in the 1920s. So what these teams actually, what these firms and research labs actually allowed you to do was collaborate repeatedly. So they gave a stable environment in which inventors could more often work together as a team. So these are the share of dyads, so the share of combinations of two inventors that file more than one patent. And again, the research labs and the firms are far above the standalone patents. What the research labs and firms also allowed you to do was to work together over longer distances. And that's what this graph on the right shows. It's basically estimating how quickly the number of collaborations between cities in the US decays with distance. So the lower the number, the faster the distance decay is, and the more local the collaboration is. What you see is that the green line has a much milder distance decay. So the collaborations in research labs decay much less with distance than the collaborations between people who are not working for a firm. That brings me to basically the consequences of this. And one consequence is how novel the patented output is. So here in this graph, what you see is this, on the vertical axis, you see the share of patents that list combinations that have never been filed before on a patent. So they're basically new combinations of technologies. And again, it's striking how this pattern changes in the 1920s. So in the 1920s, all of a sudden you see a drastic shift in innovations that are using new combinations. What is interesting is that this also holds for radically new innovations, but that starts dropping in after the Second World War. Now, if you try to link these two things together, then you can ask, to what extent are engineers actually doing more novel stuff than other workers, than other inventors? And does that depend on whether these engineers work for a firm or for a firm with a research lab? So what you see is that the engineers here, this shows you the difference in the likelihood that a patent is novel, a novel combination, between engineers and other workers. And the different dots tell you whether the engineer was working for a firm, whether he was working for a lab or working alone. So the red is alone. And there's not that much difference. So engineers do more novel stuff, but it doesn't really depend on whether they worked in a firm or in a research lab. That's very different if you look at teams. So teams are also more likely to do novel innovations than solo inventors, but teams are only able to do that if they are coordinated by firms or if they are coordinated in research labs, and especially if they're coordinated in research labs. So what I've been showing you so far suggests that there were actually two ways of innovating in the US. One was the old way with inventors inventing on their own, outside firms, with a traditional kind of job in a blue-collar worker or a craftsperson. And then the new system would be made up of engineers who worked in teams or in labs. And if you look at the time series, then you see that this second type of innovation is actually coming up very fast in the 1920s. And system one actually slowly declines. If you put this on a map, then you see that system one is, this new system, the system two, is heavily concentrated in what was the Silicon Valley of those days, right? The Rust Belt nowadays, and also in part on the East Coast. And at the same time that this shifts, that innovation shifts to the East Coast and the Rust Belt, you see that it also starts reconcentrating in fewer cities and in larger cities. So the final things that I want to show is how different societal groups became part of this innovation system. And one is one group is immigrant inventors, so people who were not born in the US. And then you see that in most of history, immigrant inventors were overrepresented compared to the local population among inventors. But it depends very much on the country. So British immigrants were always very heavily overrepresented. Sweden and Germany actually come in much later. They are also rather late industrializing countries. In Russia, you see that there's a shift when the Russian Revolution happens, and more of the immigrants are actually inventors. So you see there's quite a bit of heterogeneity. But what is very interesting is actually that there's also a lot of heterogeneity in how these inventors actually are embedded in the innovation system. So in the 1920s, you see a drop in the overrepresentation in these in the green and blue curve, which is basically the share of inventors, of the foreign-born inventors that were working for firms and R&D labs, compared to the share of foreign-born inventors that were working alone. So these foreign-born inventors were especially underrepresented in this organized science-based innovation that happened in firms and R&D labs. If instead you look at women, women were drastically underrepresented among inventors. And it goes up, especially around the share of women, female inventors goes up in during the First World War, but then it collapses again. And what is very interesting to see is also here, there are drastic differences between the two ways in which you can do innovation, like the standalone innovation, so where they would work outside, where they would invent outside firms, that keeps on rising. But there's a drastic underrepresentation of women in R&D labs and in firms. It's not unexpected given that we know what we know about this period, but it's a factor 5 difference, between 5 and 7 difference between these red lines and the blue lines and the green lines. What I found more striking is that this gap actually doesn't close. So the gap between standalone inventor shares, female inventor shares, and firm-based female inventor shares stays very high until the 1980s and then slowly starts narrowing. But even in 2000, it's actually still a 25% underrepresentation of women on firm-based innovation compared to standalone innovation. So what happens afterwards is actually that this new system of innovation loses steam. I think in the interest of time, I might skip this, so there might be at least some room for questions. So in terms of what you can conclude from this is that in the 1920s, there's a number of things happening to the US innovation system. that drastically change the way the US innovates from sort of a crafts-based innovation to a science-based innovation. So you see the rise of teams, and with the rise of teams, a deeper division of labor and new innovation specialists, the engineers. This rise of teams goes hand in hand with a new coordination mechanism that arises in innovation, namely the rise of R&D labs. And these changes, they coincide with a drastic increase of novelty that the system produces. And it's not equally accessible to all people in the US. So there's an underrepresentation of women and foreign-born inventors in these systems. Okay. There are some very interesting open questions, and that is, why does this happen in the 1920s? Because that's actually much later than the time that the US starts having engineering colleges, which happens in the 1850s and 1880s with the land grant movement. It's also 100 years later that engineers become prominent in the US compared to when they become prominent in the UK. So there's a paper by Hanlon that says that engineers explain why the UK industrialized in the early 1800s. They were very heavily involved in that. And in the US, they seem to be involved in something else, namely team-based, science-based innovation. So the engineers play a different role, but again, a very important one. Part of the explanation for that is actually World War I. In World War I, the US realizes that the Germans were actually very good at doing chemistry, and the Germans were operating these research labs, and then they started diffusing to the US. So a lot of this was also a political agenda and society turning more to science to solve some of the problems that they dealt with in the war and later in innovation. So why this system doesn't work as well anymore? That's a good question. There are a number of answers to that. One is that research labs actually went into decline in the later in the post-war periods. Maybe teams are getting too large, or maybe we need new organizational innovations. And that question is actually one of the things that we're looking at now, is to try to understand how distributed expertise works in software development, where we try to look at teams and how they collaborate on online platforms like GitHub, and how you see speciation of programmers in this world. But I think I need to stop here. So I'll hand off to you, Greg.
Interesting. Yes. So thank you very much. I'm trying to connect this stuff to kind of some of the challenges we're facing, and I'm glad you're doing software development stuff, because that's closer to the latest collaboration patterns. So then maybe in terms of connecting this stuff to what we're dealing with now, can you have any insights about how to organize things like in let's say a world of LLMs, where you have this average of society expert that anybody can work with, but it's not particularly good at anything. It's just decent at everything.
Right. So I think a number of things are very interesting in this comparison to software. So one is that collaboration platforms are actually, I think, one of the latest organizational inventions, and they are used now throughout the economy, but they started in software, like with platforms like GitHub. So they all of a sudden allowed, or all of a sudden, it was of course emerging over time, but they allowed different programmers to work together in a much more effective way. And the question is whether that also had repercussions throughout the system in terms of the specialization of workers, the places that could participate, and so on. In terms of LLMs, we are very much focused on how they might replace specific tasks, or might perform specific tasks in the economy. And I think that's probably right. So probably they affect the way the tasks that we perform ourselves. But LLMs might also play a role in how we connect to each other. So one thing that LLMs are pretty useful for is if I if I want to translate between fields, if I express, if I have to talk to people who are not in my field and they need to understand what I'm talking about, the LLMs might be able to bridge that divide more easily. So one of the things that I've noticed in my own teams is how easy LLMs have made it to enter into adjacent fields. So it's not necessarily the things that you know already very well, but you know enough to judge whether the LLM makes sense. And it then helps you very fast to discover the debates and the issues and the concepts that are used in these other fields much faster than if you had to search or read the scientific literature. So in a sense, these LLMs, they may also change the way we interact as teams.
It sounds like team evolution velocity might increase because people can just enter at a higher level.
Yes, well, they might also destroy the ladder to get into jobs, so they might take away too many of these entry-level jobs where people have the learning curves that they so far used. So to start with relatively basic tasks and then quickly evolve to more advanced tasks. So the role of LLMs in career ladders is very interesting as well, because on the one hand, they might take away these stepping stones, but on the other hand, they might make it much easier to progress because you can now interact with the LLM to learn. So I think LLMs as a way to learn new kind of tasks and become acquainted with new fields is at least that's the way we use it ourselves in our work.
Okay, so it makes a lot of sense. And now, I mean, in your study, you were looking at having organizations that are umbrellas for many researchers working together, which isn't just like a sort of centralization of effort. Whereas now it seems like decentralization is the more common role, where you have many individuals just trying stuff. And even if you have these ladders, being pulled up because this, in a big organization, there's no clear ladder to gain skills, there may be ways of individuals making progress without the organization. So I guess to what extent, is that even true? And to what extent are these online tools or collaboration tools making it easier for unaffiliated people to still collaborate?
Right. So I think in a way, what we are still in a world in which we have an increasing amount of knowledge that needs to be distributed across an increasing number of heads, so an increasing number of people. And the only way in which you can become valuable is if you connect to this collective in one way or another. So if I work in a self-sustaining way myself, so I'm basically a subsistence farmer nowadays, I wouldn't be able to have a very high productivity. I might be able to program from home and then connect to a very large body of knowledge that is out there, but that doesn't mean that I'm working alone, right? So I'm still connecting to this huge army of programmers that provide different building blocks. It's just that the interface between me and the others has become much thinner. It has become much easier to collaborate and to specialize in my own activities. So I think that's a very interesting change that has been happening. It has been happening in software. I don't know how much it is happening in other jobs, to what extent these interfaces that we need between us to coordinate our efforts with others, to what extent they have become more streamlined.
And what's the role of funding? Because it seems like having centralized funding decision-making is, one style, and with thinking just as much corporate as much as a government funding with grants and so on. How has that evolved, and and what's been productive, I guess, and where can it go?
So one of the things that I learned over the course of this project, I'm not a historian, but after a couple of years, you read quite a bit about this, is how important these research labs were, not just in the firms. They were also very important in the the academic system and in the innovation system. So if you talk to older physicists, they will tell you that some of the most interesting work at the conferences was actually presented by people from Bell Labs and so on.
Yeah.
So these research labs, they had actually something that I think people are trying to replicate in innovation policy when they talk about mission-oriented innovation. So the idea that you formulate a broad mission and then try to get as many actors to participate in that. So what these research labs managed to do is to have very broad missions. So if you think of what Bell Labs was supposed to do, Bell Labs was a monopoly, so they had all the time in the world. And what they needed to do was they needed to improve communication, which makes sense because if you're a monopoly, actually the only way in which you can make more money is if you cannot outcompete a competitor anymore. So you make more money by reducing the costs of your current products, or you somehow make products that your customers are willing to pay for more than they do now, because you already can extract all of the rent. So you want more rents, and you need to improve the productivity or lower the cost. So this mission, this very long-term mission of improving communication, was something that was very well aligned with this structure that they had. In a sense, what happened was that you had Bell Labs inventing transistors because they had switchboards that needed to be improved. They had ocean cables because they wanted most money could be earned on transatlantic communication, or even satellites and all that. Information theory came out of Bell Labs. Shannon was at Bell Labs when he did this stuff. So the other thing that Bell Labs had that we nowadays very often lack as scientists is they had all of the downstream production system that AT&T had. So they basically had if they had a good idea in the lab, then they could implement it in the engineering departments and roll it out. So there were a number of things that actually very much were aligned with having a group of people working on a pretty broad mission. With an entire, and what they mobilized was not actors all over society. They had actors within the firm. What was particularly good about this setup was that Bell Labs had to license its patents for free outside its own business. So basically everything that Bell Labs patented that wasn't within its monopoly, because in its monopoly they anyway would absorb all of the rents. But if transistors were useful outside communication, then companies could use that for free. And that, of course, was basically the start of Silicon Valley in the sense of these kind of innovations. So these research labs, there was a lot of funding, but there was also a mission. And I think that system, that kind of integrated system of innovation that they stumbled upon in this period might have been very important in pushing the frontier in technology.
Makes sense. So maybe the last question, because we're over time. I mean, nowadays we have like a tension between more centralized development thing. I'm thinking like Google's innovation with free tools, but also centralized decision making. Microsoft has Microsoft Lab integrated with the rest of the production, and other companies are trying to experiment in these spaces. Versus a lot of startups just trying various stuff, uncoordinated, but also wild. And these are two very different innovation patterns. Of course, there's also government research, which is a different template on the centralized model. So I guess where's that heading now, and what seems to be more effective?
Well, that's a good question. I'm not sure to what extent this study has much to say about that. So I think the idea of experimentation and having teams flexibly change direction, which you typically have in these smaller companies, that's a model that has proven very agile and useful for radical innovation. With the larger firms traditionally being considered to be better at more incremental innovation. But this story that has been told in the innovation literature so often actually doesn't match well with what you see in the first half of the 20th century in these large companies that had their industrial research labs. because in that time, actually, the radical innovation came out of these very large firms that were either oligopolies or monopolies. So that wasn't coming from the smallest firms. So the push to science-based innovation came from the large firms. To what extent that translates to something that we see nowadays, I find harder to judge.
Right. No, it makes a lot of sense. Well, thank you very much for the time. This was a fascinating talk.
Thank you for having me.